the one where you have a point and a slope, y minus y1 equals m times x minus x1. Not the same as slope-intercept, the mx plus b that we use a lot for graphing. That's a really big advantage there. But this guy is for finding an easy place to stick a point and a slope. When we have this, 2 points, we always start with go get the slope. Then we'll plug in a point and finish this equation. Slopage is, you got to go in and subtract y2 minus y1 over x2 minus x1. You know that formula. It's change in y. I'm going to go negative 2 minus 2, which means I have to do the x's in the same order, 3 minus a negative 1. The formula says to subtract. If that happens to also include a negative when I'm subtracting, like my number is negative, that's fine. You would have to have minus a negative in there. So I subtract those two, negative 4 over 3 plus 1 is 4. So we get negative 1 for our slope. Okay. Got to know how to find slope between 2 points, especially if the 2 points look like this. Same-o, same-o. But now you take that equation that we have, and what we do is we put y where y1 goes. We take our new, brand new m's, that's negative 1, put it there. We put the x where x1 is, and you get to choose your favorite point, and I don't care which one it is. So I'm going to go and randomly choose that one. Okay. Doesn't matter which one you pick. Put the y here. Put the x there. And it's basically done. Only thing I want is you can actually leave it in this form unless I say go graph it. Where solving for y might be helpful, but I don't want you to graph it now. I just want the equation. So you're done. It's an equation. So now I'm going to take just that one little piece of simplifying. I should probably take care of that plus or minus, or that. You know, let's call this what it is. Y minus 2 equals negative 1 times x plus 1. Awesome. Get rid of that little blip right there. There. Done. That's an equation. Perfectly good equation of a line. It just happens to be in point-slope form. Okay, next part. Do one more, and then I'll leave one for you guys to tackle. Negative 5, negative 1 is the coordinate point. 2, 4. Cool. So you start to realize that's all that really is. That's great. It looks more complicated, which is awesome, because when you show it to family members, like, hey, look what I'm working on, they see that and go, ooh. I have no idea what you're doing, but really you know it's just a point. 4 minus a negative 1 for my y is on top. My x is in the same order, 2 minus a negative 5. For a grand total of 4 plus 1 is 5. 2 plus 5 is 7. 5/7. Yes. That's a slick number. Okay, and then we take y minus, oh, eeny, meeny, miny, mo. Okay, got it. Take that one, y minus 4, got 5/7, x minus 2. We're done. Equation. This little dude, I'll leave for you. So we can get on to other fun things. Okay, so now average rate of change. So a line, an equation of a line, has crazy applications all over the place. But one of the ones, we need to talk about slope a little bit more, specifically slopes where they appear. When it comes to calculus, it's all about slopes. And we're pre-calculus. The entry into such things calculus talketh about. One of them that we get a lot of is average rate of change. Awesome concept. So let me draw you a picture. I'd encourage you to draw along with me. I'm going to draw this f of x function up here. We're going to make it kind of curvy. Oh yeah, right there. That's a good one. It doesn't have to match mine perfectly. It just has to be ballpark. So I'm going to put 2 points on this f of x curve. All right, here is f of x. I don't like when I wrote it there. Let's put it in the middle. F of x. Ta-da! Now, average rate of change introduces kind of a cool concept that we have. So I wonder if I have a tool for this. I'm going to see what I have. No, I don't want that. Do I want this? No, do I want this? No. That's cool. Weird. You guys can't see what's going on my screen, but cool things are going on my screen. Oh, it did it. Watch this, watch this. If I connect these and it's all squiggly, I'm going to connect those two dots. Watch, it's curvy. It straightened it out. Did you see that? That's neat. That little line I drew right there is called a secant line. So that thing, secant, oops, just locked something. Secant line. Right there, that thing, secant line. Really important concept. Connects 2 points on a curve, just connects them along that. You know it from circles. You connect 2 points in a circle, like 2 points on the edge of the circle, it's a secant line. Same on a curve. Connect 2 points on the curve, that secant line. Its slope is really important. Its slope is what we call average rate of change. The slope of the secant line, so I'm going to write secant slope, hopefully there's a C in there, is average rate of change. Blah, blah, blah. That is really blobby writing. Sorry about that. But secant slope is average rate of change. That's really important. Now, the concept is this. If I were to look at the rate of change at various points along here, say this little curve that I drew here, oh, the housing prices over the last 20 years, boy, have they gone up and down. All over the place. So you get the idea that they were at a particular high, then the prices dropped and up again. What we're interested in is when they're on the upswing or downswing, we're like, how fast is my house losing value? How fast is it increasing in value? And in that process, what you're asking is basically, how steeply is it going downhill there? How steeply is it going uphill there? Whew, get to that peak. Thankfully, it's kind of not changing. My house price finally is not changing because it's kind of at a level point. It's going uphill here. Oh, this is a good time right here, huh? We are living in this era right here. Prices are on the up, and they're going fast. Okay, but they went through a little modest shift in the downward direction not too long ago. So there you go. That's the idea of rate of change. All those little lines that I drew, they're called tangent lines. My little tangent lines, if I account for all of those, add them up and divide by however many I did, how many I drew, the average slope of each of those tangent lines would end up being that secant line slope. Add them up and divide by it. It's basically the average slant of that region in between those 2 points is what that secant line is. So it's pretty cool. It's very geometrical. You can just go into any 2 points on a curve and say, hey, what's the average rate of change of the slopes between those 2 points? Just connect the 2 dots. It gives you the average speed or change. So we can find that slope really easily, and we call it the average rate of change. So let's do it. We need numbers, so I'm going to throw some numbers in there. So let's do the following. To fit with your notes, this note says, hey, the average rate of change of a function, y equals f of x, between x equals a and x equals b, what that means is that that first point we'd just call a, that second point would be at b, and what this not equal to b means is that they're not the same point. They need to be disparate points. They need to be separated somehow. Okay, so that's what that's all about. That's just a little interpreting the notes business. Now I'm going to give you all an example of one we know and love. So it's also I need to give you a formula. Let me do that. So if I do average rate of change for this little picture right here, let me show you something. That little point on the y-axis, right there, this would be f of a. Okay. You see that in there? And then the height at b, f of b, represents the height at when x equals b. These two, f of a and f of b, mean the height of the function at x equals a and the height of the function f at x equals b, respectively. So what I need now to get the slope of that line right there is to take those 2 points and find a slope between them. This is the point BF of B up top here. So I'm going to zoom in there. Can I zoom in anymore? Oh, yeah, of course I can. This is BF of B, which we've seen before. We know that how that works. That's a coordinate point. And this one right here is AF of A. That's its coordinate. Oops. It's another way to look at that. So when I get in here, I'm having issues with squishing my screen. There you go, squishy squish. The formula would be for the slope or the average rate of change, the av rate would be f of b, that's the y coordinate of that second point, minus the y coordinate of the first point, f of a, all over, in the same order, the x coordinates, b minus a. It's just rise over run. It's y2 minus y1 over x2 minus x1. Right hand up y coordinate f of b minus left hand y coordinate f of a over b minus a, the x coordinates. And that's it. That's the average rate of change formula. I'm going to give you an example. So let's do one down here. Let's do x squared. We all love x squared. So cool. X squared. Got it. Let's go from -1 to 2, which would be right here. I would like to know the average rate of change from -1 to 2 on the graph of x squared. So average rate of change only works when I say that's secant lines, the average rate of change. It's the average rate of change on that interval, not anywhere else. I'm talking about just that interval. It's very specific. So I want the average rate of change between -1 and 2 on x squared. The way it would work is I'd go average rate is the slope of that line. I need to get the y coordinate of the right point and the y coordinate of the left point over the x on the right and the x on the left. Well, I got the x's. The y's I need to go find. Well, it's x squared. So if I go to 2, square that, I get 4. That's cool. And -1, square that, and I've got 1. I know those points. So I'm going from a height of 4, so that's the point 24, down here to a height of 1, because it's the point -1, 1. So I got 4 minus 1, change in y, change in height of 3, over change in x, 2 minus a -1, which is 3. So that's 3 over 3. We got an average rate of change of 1. Awesome. I love secant lines. It's crazy how simple a little drawing like that gives you the average rate of change over an interval. All the slopey slope changes that happen in there can be averaged or summed up with one little secant line. Beautiful. Okay, context problems. We got some serious context we got to visit here. How's our timing? 22 after? Oh yeah, we got time. Remember, we have this video I have to show you. It's important that you see this. 3, Camelot Apartments. Bought at $50,000 already. You know there's something questionable about the Camelot Apartments because they're selling at $50,000. Just so you know, that's probably a pretty low price for an apartment complex. Now, for tax purposes, depreciating $2,000 per year over 25 years. This thing about depreciation and taxes. All right, so let's say one of your family members owns a business. Some of you have family, direct family that own a business. If you own a business, you look at depreciation of your items that you own. So you are somebody who owns a business and you have a vehicle that's part of your business, whatever that vehicle is. Vehicles lose value, and they lose it fast. You buy a car today and try and sell it in 2 weeks, it's worth less, usually. A year later, definitely worth less. If it's your work vehicle, you can say, hey, that $2,000 a year that I lose in value in my car, that's like money out of my pocket or out of my business coffers. So what you say is, all right, Yes, I make $80,000 a year in my business. However, I lose $2,000 a year in value on my vehicle, switching